Hello. For today's presentation, we have chosen the open source project MOOSYNC, and our team is Azmeen Kausar, Haripriya, Kushal, Rithi Afra, and Swanan. Introducing MOOSYNC, an electron-based music player designed with simplicity and ease of use in mind. MOOSYNC seamlessly integrates YouTube, Spotify, Last.fm, and one can enjoy direct playback of audio files from their desktop as well. One of the MOOSYNC's unique features is its ability to mix and match songs from different providers within a single playlist, which gives complete freedom in curating your music library. For developers, MOOSYNC offers an extension API, allowing users to create their own applications on top of it. MOOSYNC was started by a team of 8 contributors in October 2021.
So for the architectural style that is used, we have observed that the open source project MOOSYNC uses the client-server style. So in general, the client-server architectural style kind of refers to a system which contains number of clients which will be like requesting resource or services from servers, and the servers will be providing them with those services and resources. In the other words, like it refers to a system which kind of breaks down tasks and workloads which is present in the whole system among multiple clients and servers which like reside in the whole system and is kind of linked together. And as you can see from the diagram, we have like different client components which are in need of resources from the servers. So for instance, we have different components like the YouTube player, Spotify player, the Last FM player, which are in need of resources from servers like the YouTube server, Spotify server, and Last FM server respectively. So as this application perfectly syncs with what is required for a client server style, we just decided to proceed with the client server style as the architectural style that is used. Next, talking about the components, the first client component is the user interface. It just acts as the primary interface for user interaction, and it's responsible for like displaying songs, viewing playlist, viewing albums, viewing the artist associated, or viewing the different genres and stuff. So it has different methods associated with it, which will eventually interact with the backend and retrieve the needed resources. For instance, we have methods like play song, which will play the song which is present in the song list, and you also have functionality to add a song to queue. And on the whole, it just provides a comprehensive set of functionalities for managing and interacting with a given list of songs. So this is all about the first component, user interface. And talking about the second component, which is the media players, you have like three different types of media players. You have the YouTube player, you have the Spotify player, and you have the Last FM player. So whenever a user searches for a particular song in the address bar, they'll be provided with a list of tabs listing if the results have to be from YouTube or Spotify or so on. So here comes the task of the YouTube player. So whenever a user clicks the YouTube tab, the list of songs which is associated with the user's search in YouTube will be displayed. So YouTube player acts as a client which is requesting resource from the YouTube server. So this is same for the other two players as well. So if a user clicks the Spotify tab, the Spotify player will be requesting a particular resource from the Spotify server. So this is all about the two components, the user interface and the media player.
Coming to the server components which are involved in our media streaming system. Firstly, there are the media providers. These usually include the YouTube provider, Spotify provider, and Last FM provider. These providers actually act as intermediaries between our MOOSYNC media players and the remote servers. So basically, when a user makes a request through the MOOSYNC player, the providers formulate the appropriate queries or API calls to the respective service platforms. They then process the responses from these platforms and also relay the necessary data back to the media players. Essentially, these are also responsible for translating and managing the communication between our users and the external media servers. And next we have these remote servers. These usually include the YouTube server, Spotify server, and Last FM server. These are actually the servers where the media content is hosted. These servers will handle incoming requests for media data such as videos, songs, and playlists. and when they receive a request from the media providers, they send back the appropriate content. It's important to note that these servers are external to the MOOSYNC and are also part of their respective service platforms. So the media providers facilitates communication between our MOOSYNC players and the external remote servers, ensuring that users can seamlessly access media content from these platforms called YouTube, Spotify, and Last.fm. This setup helps us deliver a smooth and integrated user experience. In order to understand the interaction flow between the client and the server, basically the user begins by interacting with the MOOSYNC user interface and also selecting media to play through one of the available players. So when a user makes this selection, the player sends a request to the corresponding provider to fetch the media data. Then the provider will be initiating a remote procedure call to its respective external server. It can be like YouTube, Spotify, or Last.fm for requesting the necessary media. Then the remote server processes this request and also sends the media data back to the provider. The provider then relays this data to the player, which renders the content for the user to view or listen to. Same in coming to the server response to client. The return flow of data follows the same path in reverse. Once the server sends the media data back, it first goes to the provider processes and formats this data as needed before passing it on to the player. Then finally the player takes this data and outputs the media to the user interface, allowing the user to enjoy the content. This is how the connectors play the role in the interaction of user to the MOOSYNC.
Alright, so let's take a look at the source code that corresponds to the architecture diagram that we previously discussed. The components that we will look at the source code for are the UI, YouTube player, Spotify player, YouTube provider, and Spotify provider. And the connectors that we'll be taking a look at in the source code are the procedure call connector and the remote procedure call connector. Here is the index.view file, which implements the user interface component. It is implemented using the Vue.js framework, which is specifically for building the front end of an application. In this screenshot, you can see that it sets up various buttons and other UI elements related to a song element in the application. It has buttons such as play all songs, add song to queue, play random song, and any button clicks or textual input result in the UI component sending a request to other components, such as the player component. Now here is the implementation for the Spotify player component. Based on the UI request, it invokes its corresponding Spotify provider to play, queue, and save songs. In this screenshot, the play method is shown. Here is the implementation of the YouTube player component, which is similar to the Spotify player, but it does have some YouTube specific implementation details, such as adding a sponsor block on a retrieved YouTube video so that ads are blocked. One thing to note is that both the Spotify player and YouTube player are implemented as FAT clients, since they do some processing and manipulation of the retrieved audio. They don't rely completely on the server to do any of that processing. Here is the implementation for the Spotify provider component, which uses the Spotify API to retrieve a song from the Spotify servers based on the request of its corresponding player. Similarly, here is the implementation for the YouTube provider, which uses the YouTube API to retrieve the requested video. Both the YouTube and Spotify providers receive requests from their corresponding player components to retrieve a song, and the provider components forward this request to the third-party music platform. Before forwarding the request, the provider formats the request and adds in any necessary details as required by the music platform's server. Now let's take a look at the connectors. In the left screenshot, we have source code for a player component, and we can see that it makes a function call to its corresponding provider component. This is how the procedure call connector was implemented in the MOOSYNC application. In the right screenshot, we have the source code for a provider component, and it makes a REST API call to the third-party music platform server in order to retrieve the requested song. And this is how the remote procedure call connector was implemented in the MOOSYNC application. Please note that partial code is shown for all of these screenshots, and the complete code can be found in the MOOSYNC GitHub repo based on the file paths that are provided within these slides.
Let's look at the security design patterns. Firstly, the authorization enforcer security design pattern is effectively used to ensure secure handling of user authentication and token management. As we all know, authorization is the process that performs access control by deciding whether a program or a person has the privilege to access some data, functionality, or resource. This application makes use of the authorization enforcer security design pattern to manage user authentication and access tokens. This pattern is implemented through the authflow class, which handles the entire OAuth authorization flow. Here, we are using client IDs from services like YouTube, Spotify, and Last.fm to authorize users to connect to their own respective accounts and data securely. Upon initiating the authorization process using the authorization request class, this class generates an authorization request and handles the response through a custom request handler. The class ensures that the access token remains valid by refreshing it as needed using the refresh token to obtain new access tokens without requiring users re-authentication. Additionally, by emitting events through the auth state emitter, the application can react to changes in the authentication state, ensuring that all parts of the system maintain the security compliance. This approach enforces continuous authorization checks, providing a framework for secure user authentication and access control to the system's resources. The next security design pattern is encrypted storage. This application utilizes an encrypted storage security design pattern to ensure the protection of sensitive data such as authentication tokens. This is done using the store channel class, where we handle secure storage operations for these tokens. When setting a token using the setKey method, first it's checked if encryption is available through the safestorage.isEncryptionAvailable function. If in case the encryption is supported, the token is encrypted using the safestorage.encryptString method before being saved. This is saved using the save selective preference. In case encryption is not available, then it is encoded in base64 format for storage. Conversely, when retrieving a token using getSecure method, we decrypt the stored value if encryption is supported using safestorage.decryptString method, ensuring its confidentiality. If decryption fails or if encryption is not available, we handle the situation gracefully by returning the base64 encoded value itself. Additionally, we have also incorporated error handling mechanisms like the try-catch blocks to address any potential exceptions during encryption, decryption, or storage processes. By adopting this encrypted storage security pattern, the security of the application's sensitive data is improved, mitigating the risk of unauthorized access or exposure.
So this is all about our design pattern presentation. Thank you for listening. Thank you.